Today we're going to be talking about concavity. I think you've talked about concavity in previous math classes, yes?
A little bit.
Pardon?
I think a little bit.
A little bit? Okay. So concavity just refers to the way the graph bends. Here are some examples of functions that are concave up on the portion shown, and here are ones that are concave down. I know when I was taught, if you're just looking at a graph, it's like, is the bowl up or is the bowl upside down? Okay? Now, if we were to draw tangent lines on a function that's concave up, so if we were to come in here and go, okay, I'm going to draw a tangent line over here, I'm going to draw a tangent line right there, and I'm going to draw one here, and I'm going to draw, oh, that's enough. If I looked at the slopes of those three, you would see that the slopes are increasing. Because this is a big negative number, this is a lesser negative number, and this is now a positive number. So the slopes are increasing. Also notice, and this is something that occasionally is good to know, here the tangent lines are below the graph. Using that as a justification for why something is concave up is sometimes helpful. So what would happen if the function's concave down? Well, if we draw in the slopes of the tangent lines, what's happening to those slopes? They're decreasing. And when you have something that's concave down, notice the tangent lines lie above the graph. So what do we do with all this? Well, first of all, this is just a description of concavity. This is not really a definition. The definition of concavity is something that every year I pound on students to memorize this, and students never do. I shouldn't say never. But this is important that you know that this is the definition of concavity. We're going to learn another way to test for concavity, but that's not the definition. Okay, and it's important to know the definition. If f prime of x is increasing on an open interval from a to b, then f is concave up on the open interval from a to b. So if f prime is increasing, the slopes are increasing, then f is concave up. If f prime is decreasing on the open interval from a to b, f is concave down on that same open interval. That's the definition of concavity. Okay, it has nothing to do with what the graph looks like. All that's true, but this is the definition. Now, notice it says f prime is increasing. Well, how do we know a function is, how did we test to see if a function was increasing or decreasing? What did we do all over the place on last night's homework? How did you see when a function was increasing?
The candidates test?
I'm sorry?
The candidates test?
No. You didn't use the candidates test at all on last night's homework.
Found the critical points and tested the points in between them.
To find what?
It was positive or negative.
If you said it, who was positive or negative?
The derivative.
The derivative, right? If the derivative of a function is positive, then that function is increasing on that interval, right? Well, since we're trying to find, so that's the question I just asked here. How do we test to see if a function is increasing or decreasing? By looking at the sign of its derivative. Therefore, we can check the concavity of a function by looking at the derivative of f prime. We want to know where f prime is increasing or f prime is decreasing. We can look at the derivative of f prime, which is f double prime. So this is the test for concavity. This is not the definition of concavity. Why am I making such a big deal out of that? Because when we start looking at just graphs of the derivative, you can get concavity of the original function really quickly and really easily if you know the definition. If all you know is the test for concavity, then you're screwed. Okay? And the nice folks at the College Board ask questions about this every single year, over and over and over again. And I think if they ever get to the place where everyone answers it correctly, they'll stop asking. That's frequently the way things kind of work on the AP exam. If you get ones where everybody gets it right, well, they don't ask that one anymore. So assume that f double prime of x, that should be exists, not exist, exist for all x on an open interval from a to b. If the second derivative is always positive on that interval, then f is concave up on that interval. And if f double prime is less than 0 on that interval, then f is concave on that interval. So again, this is the test. This is not the definition. So what happens in between? Well, if you have a point, capital P, whose coordinates are c, f of c, is where the concavity of f changes from up to down or from down to up, it's called a point of inflection. If you will put your pen on this and trace over it, when you get to this point, you will feel it in your hand because you'll switch from an underhand motion to an overhand motion right there at that point. They're really hard to pinpoint just by looking at a graph, right? But if you kind of trace over it, where your hand sort of switches, that's where your point of inflection is going to be. Also notice that this is going to be where the tangent line is the steepest. So let's do some examples. Find the points of inflection and intervals of concavity for f of x is 3x to the 5th minus 5x to the 4th plus 1. So let's do orange. It's October. So f prime of x is 3x to the 5th minus 5x, oh, excuse me. I'll just scratch that out. F of x is this. I don't need to write that down, but I did anyway for some stupid reason. So this is 15x to the 4th minus 20x cubed. I want to find the critical points, not of f, but of f prime. So it's just like we're a layer deeper is all. So the critical points for f prime will be found by taking the second derivative, which is 60x cubed minus 60x squared. We'll set that equal to 0. We can factor out a 60x squared and find that the critical points of f prime are at x is equal to 0 and at x is equal to 1. And what we can do is very much like what we did on your homework last night. We can use a number line to section the real numbers into 3 different intervals. And what I want to look at is f prime positive or negative in each one, is f double prime positive or negative in each one of those? So if I pick a negative number and substitute it in, and again, substitute it into the factored form, it's always faster and easier. Well, 60x squared is always positive, right? So that's not even an issue. So is x minus 1 positive or negative if I pick a negative x value? It's negative. So here, f double prime is less than 0. Between 0 and 1, let's say I pick a half, the 60x squared is still positive and the x minus 1 is still negative. So f double prime is still negative here. But if I pick a value larger than 1 and substitute it in, now the x minus 1 is positive and the 60x squared is still positive. So f double prime is now greater than 0. So here we know that f prime is decreasing. And then here f prime is decreasing again. And here f prime is increasing. So by definition, this means that f is concave down on these first 2 intervals. And here f is concave up. So the only place that f has a point of inflection is at x equals 1. Very much like sometimes we didn't have a local minimum or a local maximum at some critical point. So f has a point of inflection, and we usually abbreviate it POI, at x is equal to 1. And f is concave down on the, and concavity, unlike increasing, decreasing, it's always open intervals. So that'd be from negative infinity to 0, and again on the interval from 0 to 1. And f is concave up on the interval from 1 to infinity.
Why are they open?
Pardon?
Why are like the intervals open?
Why are they open? It's because of the way that this test is written. It says if we have the second derivative positive on this open interval, f is concave up on the open interval. And you're like, well, why is that an open interval? It's because for concavity, it doesn't make sense to look at an endpoint because you need to know, well, what's happening after that endpoint, right? You need to know, is the derivative, decreasing, or is the derivative increasing when you go past that point? Whereas with increasing, decreasing behavior, all we're interested in is, until we get to that, did it go up from any point just before it? If it did, the function's increasing. Okay? So, yeah, it's a little weird, but you get used to it. So, let's find the points of inflection of f of x is equal to x to the 5/3 power. It's kind of a weird function, but let's take a look. We'll find f prime of x is 5/3 x to the 2/3 power, and f double prime of x will be 10/9 x to the negative 1/3. So f prime has a critical point at x is equal to 0 because f double prime of 0 does not exist. Because that would be a 0 in the denominator. So our only dividing line that we're going to look at is going to be at 0. Well, if I put in a positive number into 16/9 x to the 1/3 power, I get that f double prime is positive. And if I substitute in a negative number, you take the cube root of a negative number, what kind of a number do you get? A negative. So here, f double prime is going to be negative. This means that f prime is decreasing on that first interval, but f prime is increasing on the second interval, and then by definition, f is concave down on this interval, and f is concave up on this interval. So f has a point of inflection at x is equal to 0. And f is concave down on the open interval from negative infinity to 0. And f is concave up on the open interval from 0 to infinity. And in fact, if you were to look at this graph, I always call it the kindergarten seagull, it would look something like that. Now, an interesting point. Inflection points of f occur where f prime has either a local maximum or a local minimum. Let's look at that right here. At 0, f prime went from decreasing to increasing. So that must have been a local minimum of f prime. Okay, and I know there's a lot of different functions going on here, so you have to be really careful. Let's look back at this one. Here, f prime changed from decreasing to increasing. So again, we have a local minimum of f prime, and at that point, we had a point of inflection of f. So, one of the things that the College Board likes to do quite a lot is give you the graph of the derivative of a function and ask you about the function. They like this a lot. I can't remember ever seeing an AP exam where I got to see the whole thing where they didn't have at least one question where they gave you the derivative and they asked you about the function. Fact is, usually it's several. So we want the points of inflection of f given the graph of f prime. Well, those are going to occur at the maximums and the minimums of f prime. Because from negative infinity to 1, f prime is increasing. which means that f is concave up. Is that really our bell? Did I talk that long? All right, I apologize. Just real quickly, the second derivative test, which is for local extrema. You find a critical point just like normal, and then if the second derivative is positive, which means the function must have been concave up, you've got a local minimum. And if the second derivative is negative, you must have had something that was concave down, so that must be a local maximum. Later on today, I'll work this and this last example, and I'll put it on my YouTube site. Okay? Sorry about that.